Okay, so 20-1 is on schematics and circuits. Where have you heard the term schematic before? Schematic. What's a synonym for schematic? What's a synonym? What is it?
Blueprint.
There it is. Who said it? Okay. Blueprint. Okay? A schematic is a blueprint. Now, schematics in an engineering term usually refer to electrical blueprints. Whereas if you actually had a blueprint of a building, they would say the blueprint. Okay, they wouldn't use the word schematic for that. But a schematic traditionally has to do with electrical circuitry. We are going to do 4 things. Interpret and construct schematics, like actually draw them based on what the elements are. Discuss what an open and a closed circuit is. Understand the relationship between potential difference and a circuit. And then study like the actual workings, how a light bulb physically works. Okay, how a light bulb physically works. Just to recall this information. Remember yesterday we talked about this? The way the charge carrier moves through a circuit. At the A terminal, it's got a lot of potential energy. It goes to the bulb. It uses up that potential energy. It goes back to the battery. The internal energy in the battery does work on that charge carrier, increasing its potential energy back to its starting point, and the cycle continues. Okay, so keep this in the back of your mind as we go through the process. So a simple example of a schematic diagram. Okay, here you're going to see a battery is connected to 2 light bulbs. And we're going to see on the right the actual schematic. So what do you think a schematic does? What does a schematic do for you?
Shows the movement of the electrons.
Okay, it can help show the movement of electrons, good. It doesn't necessarily show it in this one, it's not obvious, but if you know about circuits, it does show you that.
Kind of shows you where the charges are.
What do you mean where the charges are?
Like kind of where the charges would come from.
Okay,
Like,
so
where the light is.
what do you think is going on at these 3 elements here?
I'm thinking that the 2 red squiggles are the lights.
Good guess. I hope we all saw that, right? Those are the light bulbs. Go ahead.
And I think that 2 line is a battery.
Yeah, why do you think one of the lines is bigger than the other?
Positive and negative.
Positive, negative. The bigger line is the positive terminal. Okay, I think on the next slide I do all this, so you don't have to be writing down every single thing. Although I guess you could write it down about the battery. The bigger line is the positive terminal. Okay, is the positive terminal. So what is the goal, or what is the meaning to making these diagrams? Besides what they do and what the guys just told us here a moment ago, but what is the reason for drawing schematic diagrams? Yeah, a basic outline, exactly. If I have this schematic on the right, all I know is this. All I know is that there's some sort of a power source and 2 resistors in the circuit. I don't know that those resistors are a certain shape, or the light bulb is a certain model, or it's a certain brand. I don't care about that. When it comes to looking at things in terms of mathematics, it doesn't matter. It doesn't matter, for example, the orientation of the light bulb, or how long the wire is between the light bulbs. The way the wire is connected matters, but this length of wire doesn't even matter. We have no idea. So the diagram simplifies everything, and it gives us the information that is important. Again, the diagram only includes information that is useful. That's what a schematic diagram is used for.
Why is the battery so a little bit more left? Is that just random?
Yeah, just random. Absolutely. Yeah. Okay. Now, the other thing that's really important is standardization. What do I mean by standardization? And it's in the explanation up here. But what do I mean by standardization when I say that? What do I mean by standardization? We could all read this and get an idea, right? Why is standardization important, Julian?
Because if you use standardized symbols that everyone understands.
Yeah, for example, chemistry.
Yeah.
Give me an example in chemistry where something is standardized. What does everybody use the same thing?
Periodic table.
Periodic table. It's been standardized for sure. Periodic table, everybody knows it. Everybody knows there's 2 letters. Everybody knows there's an atomic mass unit. There's the number of protons. There's the valence electron charge. Okay, there's all the different ions that are listed on the right. Like, all those things are standardized, right? We know that the same thing occurs here. So if you were an electrical engineer or if you were a high school physics student, this diagram means the same thing. Okay, it is completely standardized. That's the idea behind it. Just like when we use units that are the same. That's what bothers me so much, that the world is still based on 2 unit systems. It doesn't make any sense. Why can't we all just convert over to 1 unit system, right? Shouldn't it be standardized? It would make more sense to do that, so there wasn't any confusion and stuff. Well, standardization in electrical engineering occurs. Okay, there will be small distinctions as we go along, things that could be different based on, the country of origin. Okay, but for the most part, these symbols are all standardized. All right, questions on this? Does that make sense, the idea here? Okay, because we're going to keep going with this example. Let's take a look at some of the components, symbols used, and their descriptions. All right, so first, can I get a person to read for the first one, please? The first one. Luke, awesome. First one. What do we got?
Wires that connect elements are conductors.
Because wires often
Offer.
offer negligible resistance, they are represented by straight lines.
All right, good. So wires, they are conductors. They're metal, right? What are wires usually made out of?
Copper.
Copper. Right? We talked about conductivity that day. It's copper that they're usually made out of. It's cheap and it's highly conductive, meaning it can pass on those charges very easily. So wires are a conductor. Now, every conductor has some internal resistance, just like everything has friction. But what do we say sometimes about friction? It is what? Sometimes considered to be negligible, because it doesn't really have an effect. Same thing happens here. Wires really don't show any resistance. So we say they have negligible resistance. Okay, negligible resistance. They are represented by straight lines. Okay? Second is a resistor, or what's called a circuit load. Something that can take on the potential difference in the circuit. Something that can use up the energy. That's what a resistor really is. Okay, can I get, it's just one sentence here. Luke?
Resistors are shown having multiple bends, illustrating resistance to the movement of charges.
Does that make sense analogously why there's bends there? Those bends are showing that the movement is slowing down. If I was running in a straight line and then I started running like this, it wouldn't make much sense, right? I wouldn't get anywhere. I would sit there all day going back and forth. That's what the resistor is doing. It's slowing down the current, or it's controlling the current in the circuit, thus it has those squiggly lines. Okay? Thus it has the squiggly lines. A light bulb is usually drawn just like a resistor, just put a circle around it. You don't really need to draw that little bump up there. See what I mean? So if you just drew a light bulb like this, okay, that's fine as well. Same thing as a resistor, just with a circle around it. Let's take a look at our description for a light bulb.
It goes through the same.
A resistor, a light bulb is a type of resistor, but not all resistors are light bulbs.
I know, but I'm saying,
Schematically, no.
no, when you draw
Light bulb?
schematic,
Okay.
you can just do a square line, and then you can make the,
So the squiggly line is a resistor. Squiggly line with a circle around it is a resistor that happens to be a light bulb. It still is technically a resistor. That's what I'm getting at. Okay? But it's subcategory of a light bulb. So again, here, the multiple bends in there, indicating that it's a resistor. Okay? Indicating it's a resistor. And then a bulb with the circle around it to indicate that it's a light bulb. Okay, a plug, open circuit with 2 lines on it. Why are there 2 lines on it again? The plug has? Yeah, positive, negative, or 2 prongs on it, right? Either way you could say positive or negative, or 2 prongs. One of those prongs is usually bigger than the other. Okay, that didn't happen though for a long time. Anybody know why?
Well, I didn't, some new ones don't have that.
yeah, it's kind of,
People get confused and try to put it in there because like
Well, the older ones that were not one larger than the other in prongs, you could put either orientation. I was just curious if any knew why. I don't know why. I'm curious if anybody else did. Okay, I gotta look it up.
with a plug replacement.
Why did they make plugs now with one prong bigger than the other?
They have, I guess, but,
What's that? I don't know. Maybe it has something to do with the contact surface area, but I'm curious. I don't know what it is.
with a plug, you usually replace the battery, like you usually just have one or the other in the schematic.
Let's see. Yeah, a plug could replace a battery. Yep, absolutely. I'm trying to think if they still put the voltage on a plug though when you list them in a circuit. Schematic.
Or would there ever be like a kit for the other one?
No, a plug could be used in there. Yeah, that works.
Or are they like one of those, is it like one or the other, or is it?
You wouldn't have a plug and a battery in a circuit. I mean, you could, and you'd have two sources of voltage or supply. You could really, but usually you have one power source in the circuit.
What if they have a rechargeable battery? Is there any difference?
So a battery that could be plugged in later on. So then you would have like a circuit that's being attached to something else. Sure. You don't see plugs as often in circuits as you see batteries or power sources, okay, in the actual circuitry. Let's see. Oh, well, here's the symbol reason why, but they don't actually put it physically. But see this? The EMF, the electromagnetic field that's between the two prongs of a plug, is symbolized with unequal lengths. But that's only the positive negative part that we said before. Okay, the positive negative is because they're two different sizes. Physically, I don't know why. All right, battery. So a battery, a single cell battery is what we just saw a little while ago. And a multiple cell battery is exactly what you would think. Multiple cells, one after the other. When you buy a laptop, anybody ever look at the specs on their laptop? The specs? Anybody ever notice anything about batteries on laptops? What do they say? They have battery life, but related to this. They're rechargeable.
They have lines on it?
They might have lines on them, but I don't know. What do you have to do with the second diagram, though? Lithium batteries, they're always like 6-cell batteries. Okay, the batteries are sitting in order after each other. You can A, replace one of those cells if one of the cells of the battery dies. And B, you're getting 6 times the amount of power out of the actual computer than you would out of a single cell battery. Okay, so you're going to see multiple cell batteries, that's how you would draw it, depending on how many cells there are. Like we said, the longer line is positive and the smaller line is negative. The last thing, and then we can look at actual diagrams, is a switch. Okay? We talked about open and closed real quick in class. What does it mean for a circuit to be open? Anybody remember that? I quickly mentioned it. If not, I can go over. What does it mean for it to be open?
If it's open, that means like it's preventing the flow of electricity.
Why?
Because it doesn't have like something that transmits electricity from one point to the other.
That's exactly right. Very good. That last part is exactly it. Look, take a look at the open circuit. Here's the electron. Imagine, electron, electron, electron. How's the electron going to get from here to here? Electrons can't jump in space. Granted, that's not true. They can, but in a circuit, they're not going to jump from one to the other. Okay? But the electron has to move from one to the next. So you need contact. You need some sort of conductive material that is contacting so that you can actually complete the circuit. Stop. Now, for a closed circuit versus an open circuit, okay? With an open circuit, it doesn't make sense because it's counterintuitive as to what people would say. Has anybody in your family ever said, close the lights?
Yeah. Yeah, that
Does it bother you or no?
Yeah.
Bothers me.
I sleep
Because
with
you're
lights
technically
on.
opening the lights.
It's like so much
Or opening the circuit. Right? When you say close the lights, you really just say turn off the lights. Which really means open up the circuit. That's what you're doing by doing that. You want to leave them off for a little while?
Yeah.
Yeah.
So that is opening up the circuit. When I turn the lights on, though, I am closing the circuit. Okay, so make sure you understand the counterintuitive nature of those two. All right. So, to define an electrical circuit, okay, it's just simply a set of electrical components that are connected to provide one or more complete paths. Okay, the reason you make a circuit is to complete a path that the electron can travel across, thus using the energy that the electron carries. You wouldn't make a circuit if you didn't want to use it for something. It makes no sense. So you create a circuit so that you can then use the energy of the charge carrier of that electron. Okay? Hold on one sec. So a circuit, simply put, and this is the simplest circuit that could exist, has to have two things. First, a source of energy known as a potential difference. Why do I keep using the word potential difference? Why does the word potential difference make sense? Think of yesterday's lesson. Think of yesterday's lesson. The electron started at the one terminal, right? It had high level of potential energy. It went across the light bulb, which used up the energy. It came back with how much energy now?
0.
So there's a potential difference. Does the term make sense? Because I know when I was in high school, I was like, what the hell is this potential difference thing? Everybody kept, but the teacher never told me. He's like, potential difference, potential difference. I don't know what it was. That's the reason. The electron leaves the battery with a lot of potential energy. It gets back with none. Thus, a potential difference in the energy levels. Okay? So we call battery a potential difference. Second, it has to have a load-bearing element, meaning something that can dissipate or use up energy in the form of heat, light, mechanical energy that might turn a turbine, some sort of dissipation of that energy. If I were to take a battery, like an actual battery, and connect, and we'll do this in class where we'll make a short circuit when we're doing the lab, connect just a wire from one end to the other, all you're doing is you're causing the electrons to move, but it's not going to have anything that load bearing. So what will happen to that wire over time? The wire will try to bear that load of energy, and it will in turn heat up, and you'll get what's called a short circuit. The wire could then melt and start a fire. Have you ever heard of like the houses that burn down because of electrical fires? Traditionally, they're short circuits, where there's no load-bearing element because the two wires have touched. Imagine here, ready? What if I just did this? If I, for some reason, attached an alligator clip here, alligator clips are metal prongs, and I attach another metal prong here, and then I were to connect these metal prongs. If I'm an electron, right? Electron doesn't want to hit resistance. So as an electron, I would travel out of my battery source and through the short and come right back. I wouldn't want to go to the light bulb. Remember that in general, electrons want to move on the path of least resistance. So the electron would not go to the bulb. It would say, you know what, there's a shortcut here. It's like getting back to the beginning. What's the fastest way to get back to the beginning? Take the shortcut, right? But now, all that energy that the electron is carrying, where's it going to go? It's got no light bulb to give its energy to. So the wire that it's traveling along now, that blue path, starts to heat up. It starts to say, well, I got to take this energy. It can't go on with energy forever because once it gets back to the origin, it needs to have no energy, right? Remember, the only way a battery works if there is a potential difference. If I'm at high potential energy and I go through the circuit and get back to the beginning with the same potential energy, is there a potential difference? They're the same. There's no difference at all. Therefore, there would be no reason for me to move. So I have to dissipate energy somehow as an electron. So I would choose that shorter path and cause the wire to overheat and create a short circuit. Where can this be obvious in a household appliance? How would this occur? Who can explain that? How is this simple, most basic circuit that exists relatable to some sort of household appliance? Where would the short occur? How would this happen? Or how would this look in a household appliance setup?
Toaster. That's not.
And toaster is fine, but give me more. I'm saying how would it occur?
You got it.
Nah, I have no idea.
I was thinking toaster because I mean, if you put a piece of bread in there, it may act as a light bulb to catch that energy.
Okay, now the only thing you need to be careful of, believe it or not, those metal wires that are providing heat are not conductive.
What?
Or else, do you think how many people, come on, how many people, be honest, how many of you stuck a fork in this toaster to get a piece of toast out? Right? Or something, maybe a knife, pop the toast out of the toaster or something?
They should make toasters easier to...
They're not conductive, or else people would be electrocuted all the time. They're actually not conductive. Not saying to go home and stick a fork in your toaster. Because if you do it, you could hit a part that is conductive and get electrocuted. So do not do that, obviously. Okay? But believe it or not, they're not conductive. So it wouldn't be that location, but that's a good guess there. Good guess. Where in any appliance could there be a short?
Toilet.
A toilet. I want to hear this one, because there's no electricity involved in the toilet, but let's hear it.
I don't know.
There is resistance.
There's no electricity in a toilet.
When you press the lever.
It's gravitational fluid mechanics. There's a certain amount of water in that little container. When you push down the knob, it lifts up the little valve, that water goes down, it forces the water out, and forces new water in. That's all it is.
Because like it just forces a lot of water in, and then
thought it was
forces a lot to go out.
When that thing, guys, when you push down the knob, that opens up, creating a pressure differential in the water. That causes the water to leave out another valve, and the new water that was in that little tub to come into your toilet
What
bowl.
happens when the
But
toilet's
like,
clogged?
my dad told me.
Where it's clogged, all the water coming in keeps filling it up, and there's no water to get out, so it overflows.
Man, do I have a story to tell you?
Wisdom.
Words of wisdom, let's hear 'em.
Alright, so my dad told me when we had like that stupid hurricane, which one? The stupid one, not the big one.
Super, okay.
Sandy.
No, I really. So we had a hurricane every year, my dad was like,
Yeah.
What was that?
my dad was like, we might not have like water supply or something, so we have to fill up the bathtub. And I'm like, why do we have to fill up the bathtub? And he goes, because fill up the bathtub, and then you like go to the bathroom, you just throw the water from the bathtub into the toilet, and it'll flush on its own.
That's true. She's absolutely right.
I thought it was.
You don't need power at all. You don't need anything to flush the toilet. If you, and you could test this when you get home, fill a bucket of water. I mean like a big bucket of water, not like a small bucket. Pour it into your toilet bowl. It'll cause the water to actually flow down on its own, provided there's no clog, obviously. If there's no clog, once there's a certain amount of pressure on that valve will release on its own, and it'll cause the water to actually flow down. Have you ever mopped before in your house? If you take the mop water afterward, you don't put it in the sink, you should really put it in the toilet. Pour it into the toilet will flush on its own.
So just in
Kinda
case
cool.
you like over pee, it'll flush itself.
Yeah.
I always wondered. I was like, why isn't it never filling up? That was like a lot. But
Now, if there's a clog, though, if there's a clog, anyway, next. Next. All right, a closed circuit. We defined this already. Just to have it in your notes, though. Absolutely. A closed circuit. All that has to happen for any closed circuit is that the electrons have to be able to move from one terminal to the other. Okay, one terminal to the other. Okay, it doesn't. A circuit could be closed without a resistor, and then it's a short circuit, like we said before. Oh, we didn't answer the question still, though.
oh,
How can a household appliance have a short circuit? What could actually happen?
maybe a lamp. If you turn on the lamp without a light bulb, and then you put a light bulb in, is that a short circuit?
Not a short circuit, no. You could get a current, what's called like a power surge, and the rise in current would actually cause the bulb to blow out.
What's that?
That's why the bulb blows out when you turn it on. We'll talk about it in 1 minute when we get the bulbs. It's not the bulb actually, the short. At least
TV,
a TV. What part of it though? I'm saying. How could it have a short?
the screen.
No, not the screen.
Power source.
I really don't know.
All right, think about it. Ready? You plug anything into the wall. A smart board. This dock is plugged in the wall. There's 2 prongs, which means that one prong has one wire, and the other prong is the other wire. But they're right next to each other, aren't they? Really? Inside that rubber casing, the wires are right there. If what touch? If what touch? If the 2 wires touch. If the 2 wires were to cross, okay? If the 2 wires, so imagine that the rubber casing was frayed, right? That's why when have you ever, oh, this bothers me so much, and people do it all the time. It's a fun fact. No.
Wait, so if you have like 2 Apple headphones, and you bite away the wire and then touch them together.
Alright, so hopefully they don't cause. So, imagine if this were my charger, right? On my phone, and it's connected here.
You're not allowed to charge it.
Yeah.
Is this a good example of this one? Yeah, I guess it
I
is.
have a charger with me.
You have a charger? Can I see your charger? Yeah. So a lot of people, when they wind their charger up, what do? And you think probably noisy. Anybody pick up on it?
Oh, when they put the metal thing in between 2 prongs, isn't it touching?
No, actually they're not, because they are touching it, but the rubber's in this.
It's like fake though.
That's a good idea. That's fine. That's fine. Julian, what was your guess? Oh, you have a charger. That's all. Okay. What do you think it is that bothers me when people wind their chargers? Think about a short circuit.
When you tie the
Like the rubber bunches and then it causes the wires.
you tie the knot.
They wrap it in between 2 prongs.
Not in between the two prongs.
Around.
Go around the metal of the end and the metal of the prongs.
Oh, when they wrap it around the two prongs, then it like.
Yeah, but what about the wrapping? If you wrap it too what?
Tight.
Yeah, what's going to happen?
It's gonna
It's gonna short circuit.
This starts to fray over here. People never realize it. If you take this and pull it as tight as you can and wrap it, it frays. So what you always do, my rule of thumb is I just go like this. I start with like 2 fingers there, and then start wrapping. It doesn't matter which way you wrap it. But it creates a little bit of room for like push. So it doesn't fray the ends of the wires. When the wires fray like that, you could short circuit a device. And you could actually like blow out your iPad from something like that. Okay, so keep that in mind whenever you're doing anything with a charger. Always have a little room for give in the front of the charger, especially if it's in your bag all day, right? If it's in your bag all day, that's a good way to have it wound up, so there's a little bit of room. But when the wire gets when the rubber starts to fray on that piece, if the 2 wires touch, what happens is the surge comes up like this, and it creates a power surge, and the wire could start to melt. It could also create a surge of power in your iPad itself if it's going the other direction. So when you're doing that, make sure that your wires are never frayed. What could you do? I'm trying to give you real life applications, I know. What could you do to fix a wire that is some sort of a fray on it?
Electrical tape.
Electrical tape. Good, Nina. What does electrical tape look like?
That's black.
Yeah, it's that black rubbery tape. It's not duct tape. It is not duct tape, but it's that black tape that is really flexible. You can stretch it. It also comes in many colors, by the way, among many different colors.
How come I've used electrical tape and it doesn't work sometimes?
What have you used it for?
For wire cables that are kind of ripped or shredded.
What do you mean it doesn't work? What?
It actually did not flow through. I did not.
Well, usually you use it at the end of a wire where it's like starts to fray at the end, and you like reinforce it so that if you touch it, you don't get zapped. That's the whole meaning of it, right? It's rubber, so you put the tape on there so you don't get zapped. But you're saying the circuit wouldn't work either?
Yeah, no.
Maybe something was up with the circuit, I don't know. But electrical tape should be identical in all purposes to the rubber casing on a wire. It should be. I mean, there could have been something else up, I don't know. Depends on the orientation of the situation. But it serves as like a rubber insulator on the outside.
So with Xbox controllers, the battery doesn't actually connect to the actual controller. It's got a back to it. It's like this casing that contains the negative and positive as well.
Okay.
And once I lost that back, it's like this little detachable thing from the Xbox controller. But I had batteries, and I didn't know how to connect the batteries to the Xbox controller without the actual plus or minus, like little spring thing.
Like which orientation would it have to be in? I wonder which it is, because it's 2 batteries.
Yeah, but it actually didn't have the other receptors from, because it didn't just put them in place, it like actually received the, whatever you call it, the energy or the power from it. Because it actually had the springs and then there was like the plus and minus were in the actual casing. And I lost that. So what I had to do was I used tin foil. And because tin foil is
Aluminum.
conductor or whatever it is, I could connect the batteries to tin foil to the Xbox controller. And that made it work.
That's kind of cool. I never thought about that. That's what you're talking about when you pop the case off the back, right? The
Yeah.
rechargeable ones?
Mm-hmm.
The ones with the batteries you put in? Not
Yeah.
rechargeable, the unrechargeable ones or
Yeah,
non-rechargeable?
So you could have batteries but not have those receptors.
I wonder if you could have connected wires, though, I'm wondering, from the
That's
ends
what
of
I
the
was
terminals
thinking.
to the actual things. But in the controller, are there 2 terminals in there? Or is it just one contact point?
There's the two terminals are in
In the inside? So I'm sure you could have. Depends, though, and we'll talk about it in the next section, series versus parallel. If it was a series circuit or a parallel circuit, it would impact the way you have to orient your batteries and connect them. Hold off on that thought, and we'll come back to that and see. Okay, but I'm curious if it would work. Maybe we could bring it in and see. All right, let's take a look at the workings of a light bulb. Okay, let's see how a light bulb actually works here. So can I get someone just to read nice and loud to us? And what I'll do is I'll follow along as I do this with the cursor on the board. Lise?
Current enters the light bulb through the base contact location. Charges pass through the filament and are converted to thermal, not all bulbs, and light energy. The charges, now at a lower PE, then travel from the filament and back out through the side of the metal socket.
Now notice here this is metal, like a bulb, actual contact is metal. The inner contact of a bulb socket is also metal. So although it flows in this location, it flows out of the metal socket over here. And then we can see here clearly that, look, the metal, the circuit part, the charge carrier that exits the circuit here flows through the metal into the grounding wire right here. The energy that comes in the wire that supplies the actual voltage into the battery. So although you see a bulb like this, there are still two wires coming from it. Okay, and these are the two wires that are in the actual cord in your lamp. So when you have that cord, these are the two wires you're seeing connected to the end of the actual socket, which are then connected to the bulb.
Why is there glass around the?
Why is it glass around the bulb?
No, why is there like anything around it?
You don't die.
What if it was just a film? What if there's no? Like,
Well, if you touched it, your body would then become electrocuted.
No, but like if you like you didn't touch it, it's just there, like just the wire without the glass.
Would it still work, is your question?
I mean, like why? What's the point of the glass?
Again, so it's like a protective feature, I'm guessing.
Just so you don't touch it.
Yeah, well, the thing is, nowadays, bulbs are barely even used with filaments in them. A lot of bulbs now conduct gas, the ones that are swirly. Once you develop a potential difference in them, there are gas ions in there that get excited and provide light. So it's a little bit different. And in that case, you need a glass enclosure so that the gas is still in there and there's a pressure. But here, I think there's also gas that actually occurs, or the gas that is in here. I think it's argon gas, if I'm correct. Okay, we can look it up and see, but there's a gas that's encased in the actual light bulb. Take a break if you want to take a little break. Get some water, please. Now, there's something called an EMF, okay, which is supplying your energy. And the reason I'm going to talk about EMF, and there's only a small thing I want to really notice or to write down, okay, because it's very similar to like a battery, the understanding. What we're going to do is say that the EMF is, it's what really supplies the movement. And the battery has an internal resistance in it. So, since there's a small internal resistance in the actual battery, what we could say is that the terminal voltage, the actual voltage supplied, is a little bit less than what it's read as. And this is because of this small resistance. So, when you connect a battery like a 9-volt battery, you actually don't get 9 volts out of it. And that's because of this small internal resistance that occurs in the battery. So just to jot down that even power sources that are conductors, and they have a rating, they'll have a small amount of internal resistance. Okay? A small amount of internal resistance. That was the last thing I wanted to end on, just to discuss. Okay? But again, EMF stands for electromagnetic field, and it's a source of energy, again, that can cause the current to flow, like the battery. The idea here, though, is that the EMF is slightly lower than the actual voltage of the battery. So if the battery was 9 volts, its EMF would be like 8.9 volts. Okay, because there's a small amount of resistance.